Okay, if you missed class today, the first thing that I asked students to do was do the orbital notation and electron configuration of neon, magnesium, aluminum, phosphorus, and chlorine. And just a reminder that with orbital notation, you can see that it shows the number of electrons in each orbital. In one orbital, you can have two electrons with opposite spins. And we used the rules of electron configuration to do these orbital diagrams and turn them into electron configurations. The next thing I ask students to do is to recognize what is the same in all of these electron configurations. And the thing that's the same is that they all have 1s2, they all have 2s2 and 2p6. So that's kind of a horrible drawing. So with magnesium, we could say that everything up to this point is the same as neon, and then beyond that it's a 3s2. So there's a method that I taught how to do today, and that was called noble gas electron configuration. And what you do is you put the noble gas that this belongs to. So this is the same as neon up until this point. And then after that point, it's 3s2. So it's a shorthand way to show electron configuration. Again, with aluminum, everything up until this point is the same as what neon is. So the noble gas electron configuration would have neon in a bracket, and everything beyond that is the rest of the configuration. And the pattern is very similar for each of these. And just like that. Now here's a question. What would we do to get the noble gas electron configuration of neon? Well, a lot of students suggested that we just put neon in brackets, and we can't really do that. So we need to look at which noble gas this electron configuration has in common with in terms of another noble gas. And the answer is helium. Helium is the noble gas before neon. So the proper noble gas configuration for neon would be the configuration for helium, so everything that's the same up through helium, and then 2s2, 2p6, like that. So that's an introduction to noble gas electron configuration, and we went through a whole lot of work to get this far. So the goal of today's lesson is to show you how to shorten this up, how to use the periodic table as a way to get electron configurations very quickly. So if we look at, let's see, I can get rid of that, I think, maybe not. I don't know what I'm doing. Maybe I can tug it off to the side, bring it over there maybe. Here, I'll start this PowerPoint. I gave students a new periodic table that doesn't have any writing on. And the first thing I pointed out is that the periodic table can be broken into blocks. And students took colored pencils and they went ahead and they highlighted these blocks. So the first two columns on the periodic table pertain to the S block. This middle section, the transition metals, pertain to the D block, or refer to the D block. The P block is right here, groups 13 through 18. Do notice that helium, which is number 2, the atomic number 2, would probably more appropriately be here because its configuration it would be similar to elements in the S block, but it is a noble gas, which is why it's located there on the periodic table. This P block could be extended down to include the group of synthetic elements that exist down here. They probably have only existed for microseconds at a time. And I told students to go ahead and include it if they wanted to. This could all be considered the P block. And then we have down below our lanthanides and actinides. This is called the F block. So students went ahead and labeled this on their new blank periodic table. On this slide, you can see a further breakdown of the blocks. We still have the S block here, the D block here, and the P block here, and the F block here. But now it's further broken down into rows. So the periodic table has 7 periods, which are the horizontal rows. So this is the first, second, third, fourth, fifth, sixth, seventh. And I make sure that I'm choosing the color that I want. What I ask students to do is I ask them to label what period each of these blocks pertains to. So within the S block, all of the elements in this first period within the S block, which are just hydrogen and helium, have a 1s right here. And then students label the 2s, a 3s, a 4s, 5s, 6s, and 7s. The next thing we did is we jumped to the P block. Right here is the start of the P block. So I told students to label 2p here, 3p, 4p, 5p, 6p, and 7p. I realize that got a little bit goofy there, but the periodic table doesn't have these arrows on it. When we look at the D block, you'll see that it doesn't correspond to the fourth period. The fourth period has the S block with a 4 and the P block with the 4, but the D block does have a 3 here. So the very start of the D block right here is 3D. Here we have 4D, 5D, and 6D. And down here we have 4F and 5F. So we labeled these things on our periodic table, and you'll see in a little bit how this will be helpful to us. The next slide shows how these things can be broken down into groups or columns on the periodic table. And what I'm going to do is I'm going to go ahead and label like I had the other 1s, 2s, 3s. Okay, this was a 3D, 4D. It's not the most ideal here. 5D, 6D, 2P, 3P, 4P, 5P, 6P, and if we were going to continue, this would be 7P. Those are those synthetic elements that we don't really talk about much. And then we have 4F and 5F. So what you notice here within the S block, all elements within this first group on the periodic table will end in an S1 in terms of an electron configuration. All of the elements within the second column will end in an S2. Within the D block here we have D1 through D10. Within the P block here we have P1 through P6. So I instructed students to go ahead and label all of these on their periodic table as well. And the periodic table that I gave in class gets kind of crowded in here to label the Fs. So I told students they could if they wanted to. We typically don't do a lot of configurations within this S group. So this is the extent that students labeled the periodic table today: the S block, the D block, the P block, and the F block. if we look at the periods, we can have our 1s, our 2s's, our 3s's, 4s's, and so on, our 3d's, 4d's, 5d's, 6d's, our 2p's, 3p's, 4p's, 5p's, and 6p's, and so on. And this may not make sense right now in terms of like, what are we doing this for? Why are we even doing this? And let me just show you how we can use the information right here to get to an electron configuration. I'm going to choose the element arsenic here. Arsenic has 33 electrons. And I could make orbital diagrams and put all of the electrons in, but I'll show you how to use the periodic table to get it. So what we do is we look at our destination element. This is arsenic. And we start at the beginning, go all the way to the beginning, and we just work our way across. So we have a 1s2. All right, we're not at our element yet next, so I'm going to go to the next row. 2s2. I'm going to go over here to P6. I'm still not at the element that I'm looking for, so I'm going to go down to the next row. 3s2. 3s2. 3p6. Still not there. Going down to the next row, 4s2. And 3d10. And then we are into getting close to our element, so we have a 4p1, 4p2, 4p3. So this is the configuration for arsenic, and you can see how I just used the periodic table to get that. Getting the noble gas configuration is very easy. All you have to do is look at the element that you have here, find the noble gas that's right above it, put that in brackets, which is argon in this case, and then go ahead and start from here. So argon, and then 4s2, 3d10, 4p3. 4s2, 3d10, 4p3. So you can see here that the highest occupied energy level is the 4th energy level. So if I ask how many valence electrons there are in the 4th energy level, we would count all of the electrons that are at the 4th energy level, and there are 2 here and 3 there, so there are a total of 5 valence electrons. So this is where I'm going to stop this video today. I will do more examples in class, and if you have any questions, please feel free to ask me, and I would be happy to answer them for you.